When it comes to solids, solids fall into two categories. Either you consider it a crystalline solid, where you've got this repeating pattern throughout the crystal, or you're an amorphous solid, where you don't have a long range order. Like you may have a short range repeating pattern, but over the entire solid, you don't have this um, repeating pattern. So when we're dealing with crystalline solids, there's going to be several types, and there's going to be several shapes in terms of repeating patterns. So amorphous solid, this is like wax and glass and plastics. So we're not going to, talk anymore about that. They're solids that don't have a repeating pattern, whereas crystalline solids have this repeating pattern. All right, a cell unit is the basic repeating pattern of a crystal. So it's this pattern that repeats itself over and over and over. Lattice points are the things that define the repeating pattern. All right, so you could have atoms or molecules or metal atoms at the lattice points. Oh, and ions, right? You could have ions, right? You could have sodium ions, chloride ions, right? Some sort of cation anion combination. All right, so there are no lines when we're talking about this repeating pattern, right? So if you go back to this drawing right here, you got to visualize no lines, right? So the lines are just there to, help us see the repeating pattern. And those lines represent either Coulombic attractions, covalent bonds, or some sort of metallic bonding situation. All right, so as far as the repeating patterns go, they can be broken up into 7 different categories. You're either considered cubic, teragonal, orthorhombic, monoclinic, triclinic, hexagonal, or rhombohedral. So with simple cubic, side A, side B, side C are all the same length, and you have 90-degree bond angles between all of the different sides. Teragonal, 90-degree bond angles, but one of the sides is a different length. Orthorhombic, you have 90-degree bond angles, but none of the sides have the same length. Or you could be rhombohedral, where all the sides are the same length, but one of the bond angles is not 90. Monoclinic, none of the sides are the same length, and you also have a situation where you have a non-90 degree bond angle. Triclinic, none of the bonds are the same, and you've got a different orientation in terms of that non-90 degree bond angle. And then there's hexagonal, where A and B are the same length, but C is different, and you've got a 120 mixed in there with the other 90s. All right, within the simple cubic, or within the cubic pattern, there are you can be subcategorized. All right, you can be subcategorized where you're just plain cubic, or you could have a extra lattice point in the inside, or you could have an extra lattice point on one of the sides. So simple cubic, body centered cubic, face centered cubic. So when you have simple cubic, all right, you just have 8 lattice points defining the shape of the repeating pattern. With body-centered cubic, you get this extra lattice point in the middle. Whereas with face-centered cubic, you get an extra lattice point on each of the sides. So 5 dots defining a side rather than 4. All right, so we get different metallic. Well, I guess that's it. With metals, you can have all of these types of crystals represented. It's about how these atoms pack together as to whether you get these different repeating patterns or not. All right, and this is called closest packing. And as far as with the shapes are concerned, and with closest packing, we're not going to spend a lot of time time on it. Just suffice it to say, it depends on how these atoms pack together, and that depends on the size of the atoms or the ions that are packing together. And you get these different repeating patterns that give you these different cell shapes. All right, the thing we're going to mostly focus on are the different types of crystals. And that's not defined by the shape, it's defined by what kind of bond holds it together. So a crystalline solid is either held together by some sort of Coulombic attraction, a covalent bond. You could have a molecular crystal where at the lattice points you've got molecules, and this is held together by some sort of van der Waals force. Dipole-dipole, hydrogen bonding, induced dipole. And then there's metallic bonding, where you get that special kind of delocalization of these overlaps within the covalent bond, and you get metallic bonding. So ionic crystals are composed of ions at the lattice points, all right, held together by Coulombic attraction, and as we know, these would be hard crystals to pull apart. Ion-ion attractions are strong. Poor conductors of heat and electricity, all right, so until you melt the crystal, then it'll conduct electricity, but as far as electrons being able to move through the crystal, they're not allowed, all right. The electrons are localized on the different lattice points, and electrons aren't allowed to move through these crystals. All right, so we're maximizing electrostatic attraction, minimizing repulsion. Let me go back. Maximizing electrostatic attraction, minimizing repulsion. So if we have cesium chloride, we end up with a face-centered repeating pattern where you've got the big chloride ion in the middle surrounded by small cesium ions. So again, all the different cell shapes are represented with ionic crystals. Atoms occupy the lattice points when we're talking about covalent crystals, right? So atoms at the lattice points, and it's held together by covalent bonds. I mean, this is the thing that defines a covalent crystal. And as we know, covalent bonds are strong, so covalent crystals are hard to pull apart. Very high melting points, high boiling points, very hard to pull apart. Diamond would be an example of a covalent crystal. Again, electrons are considered localized, so electrons aren't allowed to move around through the crystal, so poor conductors of heat and electricity. There we are, diamond. So we get a tetrahedral geometry around each of the covalently bonded carbons, right? So it's sp3 hybridization around each of the carbons in the crystal. So you can think of it like a covalent crystal is like one massive molecule, just huge. All right. Another word for a covalent crystal is a network solid. All right, so the other kind of carbon is graphite, and instead of being sp3 hybridized carbons, you get sp2 hybridized carbons. So you think about benzene, right? sp2 hybridization, you get this delocalization around the ring. Well, instead of those carbons being bonded to hydrogens, think of each of those benzene rings being bonded to another benzene ring. So you have these flat sp2 hybridized carbons forming plates. All right, so when we talk about graphite, right, you slough off the plates. So the interaction between the plates would be induced dipole, a weak interaction, but the plates themselves are covalently bonded, hard to pull apart. So this is the nature of graphite, right? It sheaves off or sloughs off in layers. Hard to pull apart the layer, easy to break the layers apart from each other. Oh, there it is. Van der Waals forces, right? Induced dipole. So with molecular crystals, we have molecules at the lattice points held together by van der Waals forces. So, ice would be an example of a molecular crystal. At the lattice points, you'd have waters. Solid ammonia, you'd have ammonias at the lattice point. solid sugar. You'd have sugars at the lattice point, and what would hold the sugar together would be the hydrogen bonding and induced dipole effect between the sugar molecules. Again, electrons are not allowed to move through these crystals. They are poor conductors of heat and electricity. Easy to pull apart a molecular crystal, right? So if I want to separate the sugars, I'm just breaking van der Waals forces. So easy to pull apart, easy to melt, easy to boil. Solid CO2, right? CO2 is at the lattice points. It's a nonpolar molecule, so easy to pull solid CO2 apart. Solid CO2 is dry ice. All right, metallic crystals. All right, so this is where I think we describe, this metallic bonding, which is a strange phenomenon with metallic crystals. So you have metal atoms. Well, actually, you have at the lattice points with metallic crystals are the core electrons of the metal atoms, and it's the valence electrons that are delocalized throughout the lattice. So this is the one type of crystal where electrons are allowed to move through this, what we call sea of electrons. All right, so a metallic crystal is the ultimate in delocalization. Valence electrons are not owned by any particular atom. They're shared throughout the crystal. So when you have solid sodium, right, that one valence electron is not owned by any particular atom. It's shared throughout the entire crystal lattice. This overlapping, this delocalization of electrons makes for a very high melting point, right? Hard to pull apart. Malleability, ductility, high melting point, good conductors of heat and electricity. These are all a manifestation of metallic bonding, this delocalization of electrons throughout the crystal. So this is my rendition, right? We've got the core electrons and the nuclei at the lattice points, and the gray area represents this mobile sea of electrons, right? This overlapping of valence levels so that the valence electrons are shared throughout the crystal. When you get to the molecular orbital model, right, this is where we can describe this. So it's an overlapping of molecular orbitals. So you end up with filled molecular orbitals and you end up with empty molecular orbitals. So the electrons have some place to go now, right? They can go into the empty molecular orbitals, right? So when you put a metal into an electric socket, the electrons have some place to go. They can go into this overlap between within this molecular orbital bonding scheme of the metallic crystal. So again, conductivity, malleability, ductility, all properties of metals due to this delocalized overlapping of molecular orbitals. All right, when dealing with metals, they can come as a mixture, right? So metals don't react with each other, but they can be mixed together to give a metal with a different property. So there's two kinds of alloy you can run into. One that's called a substitutional alloy, where literally you take metal atoms of roughly the same size and you replace some of the metal atoms of one type of metal with another type of metal in the crystal, and you end up with a mixture of different atoms of the same size. You're literally substituting atoms in the crystal with a different type of metal atom. Brass would be an example of a substitutional alloy. All right, so you're mixing copper and zinc atoms. They're about the same size. So 2/3 copper, 1/3 zinc, you get brass. Sterling silver. All right, so one way to keep silver from being so reactive is to mix some copper in with it. So if you mix in some copper atoms into the silver crystal lattice, it helps the silver from being so reactive, right? You keep your silver longer with sterling silver than you do with pure silver. So substitutional alloy, I take the zinc atoms and replace them in the copper lattice to get brass. All right, interstitial alloy is different. All right, so we end up with two atoms of different size. Now, it doesn't have to be two metal atoms. It could be a metal atom and a non-metal atom. What happens is, as these atoms pack together in a crystal, there's spaces between the atoms. So for example, with steel, you've got big iron atoms where you've got little holes between the iron atoms as they pack together. And in those holes, you can put carbon atoms. Smaller carbon atoms can fit in these holes and make it less malleable. All right, so a little bit of carbon mixed in, you get, steel that's somewhat bendable, but less bendable than iron. Medium bendable, all right, so you put more carbon in there. If you want tool grade steel, you get a 0.6 to 1.5% carbon mixed in with the iron. Now, there's a limit to this, right? We want iron because iron's malleable, it's bendable. If we put too much carbon in there, then it becomes brittle, right? And the crystal, it won't be metal anymore, right? It'll crack like an icicle or something. So it's about mixing the right amount of carbon in there to make the metal hard, but not brittle. So like I say, the big iron atoms, when you pack them together, there's spaces between the iron atoms, and in those spaces you can put the carbon atoms. So substitutional alloy, something like 14 karat gold, you're replacing some of the gold with some silver. All right, so some of the silver atoms are interjected into the crystal in place of some of the gold atoms, and with steel, between the iron atoms, you're fitting in some carbon. So know the difference: substitutional alloy, interstitial alloy.